Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will continue to examine multiple resistor circuits, and in fact in this one we will examine multiple resistors in series and in parallel. Okay, so now that we've sort of looked at multiple resistors in series and multiple resistors in parallel, we need to be able to handle circuits that look like this, where you have some resistors wired in series and some resistors wired in parallel with one another. And for this circuit, I'm going to ask that you do the same as before. So solve out the full circuit, and you're going to pause at the end of this introduction, try it out, and then see how you did. So here's my advice for solving these, okay? The first thing you're going to want to do is remember that for any resistors that are directly in series or directly in parallel, you can combine them and make a simpler circuit. So the way you want to handle this kind of circuit is take R2 and R3 and break them down. So what is the equivalent resistance, R23, of this thing? And if you draw the equivalent circuit, right, so with R1 in series with these two resistors in parallel, you should be able to solve the circuit. Note the way that I'm sort of describing this. I would say R1 is in series with the combination of R2 and R3, which are themselves in parallel with one another. All right. Okay, so how do we go about solving this problem? First things first, as always, fill in the information we know. So 4 ohms, 3 ohms, and 2 ohms drop right in, okay? We also have our 12-volt EMF. Notice I haven't had you go the other way yet, although that is something you should be able to do. So if you're given other parts of this grid, you should be able to sort of back your way out to the individual resistances, but let's start here for now. All right, so first things first, we want to find the total equivalent resistance of these three resistors together. And to do that, we'll break it down into two steps. The first is finding R23, the resistance of the two resistors in parallel. So 1 over R23 is equal to 1/2 plus 1/3. And therefore, R23 is equal to 6/5. 6/5, that's 1.2 ohms. Then that 1.2 ohm effective resistance is in series with this 4 ohm resistor, R1. And therefore, the total equivalent resistance of this whole combination is 5.2 ohms. So that goes in directly. We can then take the total potential difference, or the EMF, and divide by the effective resistance, or the equivalent resistance, to get the current of 2.3 amps. All right, so far so good. Then what do we do with that? Well, we know that same 2.3 amps, okay, is going to be also the current through R1, all right, because the battery and the resistor R1 are in series with one another. So we can say that this 2.3 amps is also the current through R1. Because we can say that, now we have the resistance of R1 and the current of R1. That gives us the potential difference across R1, so delta V1. And we can get that using the definition of resistance. 4 times 2.3 is equal to 9.2 volts. All right, now we have this. The potential difference across R1 is 9.2 volts. We also know that the EMF is 12 volts. So if the EMF is 12 volts and the potential difference across R1 is 9.2 volts, then the potential difference across R23, both of them, okay, from here to here, is going to be equal to what's left over. So 12 minus 9.2 volts is equal to 2.8 volts, okay? Now that we know this is 9.2, this is 2.8 and 2.8, we can take our delta V's and divide by the resistances. So 2.8 divided by 3 is 0.9 amps, and 2.8 volts divided by 2 is 1.4 amps. And we double check, does 1.4 plus 0.9 equal 2.3? Yes, it does. Excellent. Okay, so that gives us our full grid here. notice there's actually more than one way through this grid, but that was what I found to be the most straightforward. Then you're going to find the power. As always, once you have this full grid, it's pretty straightforward. Again, I'm going to use I times delta V, and that gives me the power in R1, or the power dissipated in R1, in R2, and in R3, and in the total circuit. Notice here, the power dissipated in R1 is much, much, much bigger than the power dissipated in either R2 and R3. And that's fundamentally due to a couple of things. One is, by placing R3 in parallel with R2, okay, what we've done is we've reduced the effective resistance of this total thing. Okay, this thing together is only 1.2 ohms. And because it's only 1.2 ohms, it's only getting basically 1.2 divided by 5.2, about 1/5 of the potential difference across both of these things. So the potential difference, most of the potential drop, goes to this higher resistor, R1, and only a little bit, 2.8 volts, is left over for these two resistors together. As a result, the power delivered to R1 is going to be much bigger than the power delivered to either of these two resistors.